let us look deeper into the K-means clustering. So there are three more things I want to discuss with you guys. The first one is about the distance measure. So far, we're calculating the distance in the easiest way by calculating the one-dimensional distance is the absolute value between the two objects in a two-dimensional space. We are considering the Euclidean distance by default. I did not even mention about those. But how can we use some different distance measures to calculate in terms of different data types or different measurements that we are desire or the distance that makes most meaningful things into the application domain? Then we also can discuss about the distance between clusters. What's the distance between clusters and clusters, or how can we really calculate an object with the existing cluster, find the best distance representation. Finally, we can have a different concept looks into the centroid location. In terms of the centroid location, which is what we use for K-means clustering. Remember, I keep mentioning there's another clustering called K-medoid approach. So what is the major difference between the two? These are all the things I want to discuss in this video. So, distance, similarity and dissimilarities. Distance are normally used to measure the similarity or dissimilarity between the two data objects, and obviously this is the most important thing in K-means clustering because those similarity and dissimilarity are the main two criteria we want to implement here. So there are some popular including Minkowski distance. What it looks is going to take a square root of the Q value, and then we calculate the distances between different attributes and then take the Q powers of that. And after that, we sums up all of those things inside of a square root for that value. So if we say that when Q equals to 1, which means the simplest format, and that is going to what we call a Manhattan distance. We calculate the absolute values between all the attributes and simply sums them up. This is one of the most easy way of calculating the distance as well as most effective way. When Q equals to 2, that is what we call the Euclidean distance. And of course, Q can go to any different values using the same structure, and it will generate some distances for us. So one can also use the weighted distance, parametric Pearson correlation, or other dissimilarity measures, including the things that we have discussed previously, which is the Jacquard distance. Since we have mentioned about those things originally, I don't want to spend extra time on this one. In this slide, use a slightly different representations in terms of what we use of the PQR over there. In here, M11 represents the total number of attributes where A and B both have value of 1. This corresponding to the value of P in the previous slide. M01 represents the total number of attributes where attribute of A is 0 and the other attribute is 1. So you can see that use this 01 to represent it. I found this probably even easier to be understood. M10 represents the number of attributes where attribute of A is 1 and attribute B is 0. So we will be able to calculate those values one by one, and then we can calculate the Jacquard distance, which is M01 plus M10 divided by M01 plus M10 plus M11. So this is what we call the Jacquard distance. The opposite value of that is Jacquard's coefficient, so the upper part has been changed to M11 instead of M01 plus M10. And you can see the Jacquard's distance sums up Jacquard's coefficient will always equals to 1 based on the definition. And of course, one more thing I want to reiterate is that M00 is not used in the Jacquard's distance nor coefficient. It has been used in the Pearson correlation coefficient. So these are the major things that we have been used in the binary data set. So of course, this gives you an example that you should be familiar with already, saying that I have some binary data sets. We have 7 customers and their age is going to be given, income, zip code, and gender. Based on this data set, if you want to do the clustering, you can still do the clustering by calculating the distances, since we have the Jaccard's coefficient or Jaccard's distance or even Pearson correlation coefficient to use, and we will still be able to generate clusters based on the k-means clustering. So this gives you the idea that as long as you have the distance measurements, you will be able to calculate the distance between all the objects so that you can form the clusters. Besides that, the distance measure, we can also have some different perspectives to calculate the distance between the clusters, no matter is a point to a cluster or a distance between clusters and clusters. Let's take a look at this. There are 3 different kinds of ideas that can be represented. Based on what we have seen so far, the average is the things that we have been using, because we use the center of the cluster to represent the cluster. So when we calculating the distances, saying that from one point to the cluster, we calculate the distance from that point to the center of the cluster. However, there are some other alternatives are available, starting with what we call a single link. What this is trying to do is it calculate what is the smallest distance that you can find from this point to the cluster or from this cluster to that cluster. Because you can see that one cluster is composed of several items. Of course, you can use the average or the centroid to represent the whole cluster. However, in fact, you may end up in this cluster. You may have one point that's far, far, far away, -100, still belonging to this first cluster. And that will change a lot of things over there. In the end of this video, we actually want to talk about the k-means clustering. One disadvantage of k-means clustering is that it is sensitive to outliers. Like I said, if I have a -100 in this whole data set, it will change the whole structure about the clusters. So that's something we don't like. And therefore, we have some other things to help us think or try to understand the cluster. So single link, again, is the smallest distance between an element in one cluster and an element in the other. Complete link means the largest distance between an element in one cluster and an element in the other. Average is what we have been used so far. In other words, if saying that I want to find a distance for a single link concept, say I want to find an item that's x equal to 21, located at 21 location, and I want to calculate the distance between that point to cluster number 1. When we do that, you can see that what we use is that we use 21 to minus every single point over here to find the distance, and the one that we're going to assign is the closest one. In this example, we can easily visualize that the closest one is going to be generated from the element 9 inside of cluster 1. So the single link distance between x equal to 21 and C1 is 12. For the complete link, then we want to find the largest distance, which is 21, goes all the way to the first location of element 2 over here. So the distance for a complete link is going to give us 19. The average is calculating from the element to the centroid. So that is like considering for one single element with a cluster. One thing you can understand that even though that's one element, that can still be considered as one cluster. It's just that this cluster has only one item. On the other side, if we are calculating the distance between clusters, so C1 and C2, see that the closest distance can be generated by node 9 and node 10. So that's how close they are by looking into single link distance. You can see that the two clusters are actually very close to each other. When we look into complete link, then we can understand what is the largest distance between the two, and therefore the largest distance is going to be 19 minus 2, or 2 minus 19, and take an absolute value equal to 17. The average distance would be the two centroids locations distances, and therefore 9.33 is what we see over here. So that gives you a different perspective of how would you be able to see the distances between two clusters, or a clusters and an element. So finally, we want to look into the centroid location. Well, at this stage, you know that the centroid location is always calculated by the average location of all the elements belonging to a cluster. That is basically a given value, given equations like this. Sum of those values are one attribute at a time divided by the total number of elements belonging to a cluster. So you can calculate the x location. By doing so, you can then calculate a y location by doing so if that's a two-dimensional space. If that's a three-dimensional space, you can calculate the third value, etc. However, you need to understand one thing. The values calculated through this approach is basically a synthetic location. It may not really reflecting the values in real life. That's why a further concept has been proposed. Based on our previous video, you see that after 20 years, the Medoid idea is being given and then created K-Medoid algorithm to say improve the K-means clustering. So what is Medoid? Medoid is basically the centroid concept with one more step. Once you find the centroid, now write a for loop. Use the centroid to calculate the distance with all elements in this cluster and find the closest one. That one is a real value, and use that real value to represent the whole cluster. So you see that creates one more step, but it actually can bring the synthetic centroid location to reality. So for K-Medoid algorithm, it's actually doing the same thing. Originally, you have all the data, you randomly select 3 data. So all those 3 data, say k equal to 3, are real data. So use those 3 data, calculate the distance with all existing values you have from 3 clusters. Then you can calculate the centroid of each new cluster. But before you use that centroid to do the repeat process, you add one more step, find the closest one, forming what we call the Medoid, and use the Medoid to calculate the distance with all existing items. Repeat the whole process until Medoid don't change, and that is what we call the Medoid algorithm. So this is what we would be able to see. The concept is exactly the same. It's just adding one more concept over there to represent a more realistic centroid center of the cluster. So you can see that Medoid, one chosen centrally located object in the cluster. So finally, let's summarize what we have learned in the K-means method. The strength of the K-means clustering is that it's super simple. The idea is very easy. More importantly, the big O analysis is fantastic. See that if you truly understand the K-means clustering, the big O analysis is T multiply K multiply N. N is the data size that you have. So N is here. If we ignore T and K, you can see that this is actually a linear algorithm, and that is fast. K indicating how many clusters that you have. So obviously, if you have more clusters, the more calculations at every single point need to calculate. It's getting more calculations over there. So K is a constant value though. That's a user predefined value. T indicating that how many times that you need to do the iteration. Sometimes you can, like we said in the algorithm, you can move until there's no change. However, when the data set is huge, you may not have that luxury, or the value never converge. So you can also predefine an iteration, say 10 times. just run 10 times. I want to get a rough estimation. I don't really need to find a global maximum. I want to find something that can give us a quick, reasonable amount of time, but accurate results. So you can see that T and K are relatively smaller, much smaller than the data size that you usually have. So you can understand K-means clustering is actually a linear algorithm. However, it of course has some disadvantages. First of all, applicable only when mean is defined. Then what about the categorical data? Remember, we were looking at a binary data set. So when that's happening, how can we really find the center and find the representative one? So of course, in that case, medallion is going to be a more suitable way. And that's another deeper topics that we can look into. Need to specify the number of K. That might be the most biggest issue that K-means clustering, because you need to have some pre-knowledge about that. And what if your guess is not correct? So in K-means clustering, when we are really doing research, we need to try multiple of Ks, and that of course increases the complexity of the big O analysis. It is unable to handle noisy data and outliers. Like the examples we see, if we have a very large data, all the point will be skewed over there, or itself will form one point cluster, and that is probably not something we are interested in. It is also not suitable to discover clusters with non-convex shapes. So convex shapes indicating like a circle or a spherical continuous location surfaces that we are interested in. Therefore, there are many other improvements available to tackle different approaches over there. While we go deeper into clustering, we will see different variations. We will see they can solve some of these problems, but creates more problems. So the K-means clustering algorithm is sensitive to outliers, and that's why when we using the K-medallion approach, it can alleviate that problem, because when the synthetic centroids are found, while we add one more step to find the closest element, we can reduce the effects of the outliers. So instead of taking the mean value of the object in the cluster as the reference point, medallions can be used, which is the most centrally located object in a cluster. So you can see that by using the K-medallion approach, we can kind of alleviate the problem of the outlier. But we still need to specify the number of K over here. And this gives you a deeper look into the K-means clustering.